Session. Today, we're going to explore a very important concept in software design, how we can view a system as a series of transformations on data. Think of this as a factory assembly line. Each station in a factory takes some raw material, processes it, and sends it to the next station for further processing. This is exactly how data flow in certain system architectures. Let's break this down. The key idea here is that the system is decomposed into a set of components or elements, where each element is responsible for transforming input data into output data. These transformations are independent of each other and can happen sequentially or in parallel. Now, let's break this concept further with examples. Imagine you're writing a simple text processing application. The task is to take a text file, clean up unnecessary spaces, convert all characters to lowercase, and then save the cleaned up version to another file. Here's what happens. 1. Input. You start with a raw text file. 2. Step 1, a function trims the unnecessary spaces, transformation 1. 3. Step 2, the result goes to the next function that converts the text to lowercase, transformation 4. Step 3, finally, it's written to a new output file, transformation 3. This is a linear data flow because data moves step by step in one direction, and there are no cycles. Each component or function performs one transformation. Now let's consider a slightly more complex case, like a feedback loop in a control system. Say for monitoring the temperature in an oven. 1. Input. The current temperature is fed into a monitoring system. 2. Step 1. The system checks if the temperature is too high or low, transformation 1. 3. Step 2. If it's too high, the system sends a signal to turn off the heat, transformation 2. 4. Step 3. Once the heat is turned off, the system rechecks the temperature, and if it's still not within the correct range, it keeps looping until it is. This is a graph with cycles because data goes through transformations, but can be fed back into the system for further adjustments. A tree structure might be useful in decision-making systems. Let's say you have an app that recommends workout routines based on user input, like their fitness level and goals. 1. Input, the user enters their fitness level beginner, intermediate, advanced. 2. Step 1, based on that, the system breaks down into 3 different branches, one for each fitness level. 3. Step 2, from there, each branch breaks down further based on the user's goal, e.g. weight loss, strength training, endurance. 4. Step 3, based on the branch, the app recommends specific routines. Here, data is flowing through a tree structure where each decision leads to more specialized choices. Finally, let's talk about how these components are connected. The connections can take several forms. I/O streams, like reading data from one component and passing it directly to another, such as the stout to stdin in Unix pipelines. Files, data might be written to a file by one component and then read by another. Buffers, used to store intermediate data temporarily while it's being processed. Pipes, similar to I/O streams, but used for real-time processing. These connections allow data to move through the system, no matter what structure the data flow takes. In summary, data flow architecture allows us to design systems where data is transformed step by step through a series of components. Whether it's a linear pipeline, a cyclic graph, or a tree structure, the main point is that each part of the system works on the data independently and passes it along. Think about this the next time you're working with a system that processes data, whether it's a real-time application like a video streaming service or a batch system like payroll processing. Let's take a look at this block diagram of a typical data flow architecture, as shown in figure 5.1. In a data flow system, data moves between subsystems, which can be represented as blocks in this diagram. Each block or subsystem performs a specific transformation on the input data before passing it to the next subsystem. The key principle here is that subsystems are independent. They don't need to know about each other's existence, as long as they maintain compatible input and output formats. This independence allows us to swap out or modify individual subsystems without affecting the rest of the system. Let's break this down with a few key points in an example. As you can see from the diagram, each block or component operates independently. The only requirement is that it accepts data in a compatible format from the previous block and outputs data in a format that the next block can process. For example, in a text processing pipeline, one component might clean text and another might analyze it for keyword frequency. Each component does its job independently of the others. Because these subsystems don't depend on the internal workings of others, You can easily modify or replace a subsystem if necessary. For instance, if you wanted to change the method of keyword extraction, you could substitute the relevant block without rewriting the entire system. This makes data flow architectures very modular and easy to maintain. Notice that the topology of the system can vary. It could be linear, like a pipeline, where data flows sequentially from one block to the next. It could have cycles where data is fed back into previous subsystems for reprocessing, as shown in the loop on the right. Or it could be branching, where data splits into multiple paths, like the diamond-shaped connections in the center. Despite these variations, the core principle remains the same. Each block transforms data independently and passes it along. Let's think about a video processing system as an example. Say you're building a system that applies multiple filters to a video. Input video, the raw video file is the input. Step 1, the first block might reduce noise in the video denoising. Step 2, the second block adjusts the color balance. Step 3, the third block compresses the video for storage. Each block performs a transformation independently and simply hands off the processed video data to the next block in the system. So, to summarize, data moves between subsystems without interaction except for the input-output connections. Subsystems are independent and can be substituted if they maintain compatible input-output formats. This design enhances modifiability and reusability, making it a robust choice for systems that need to evolve over time. We can now dive into some specific examples of where data flow architectures are used in real-world applications. Any questions before we move on? Now that we've talked about data flow architecture, let's dive deeper into different ways of connecting module outputs to inputs and how that affects the overall data flow patterns. There are multiple ways to connect these modules, and each connection results in a distinct data flow pattern. These patterns dictate the execution sequence, or the order in which the database's arrays are supported as a native data type, making it easier to represent things like time series data or large data sets. Example: in a weather monitoring application, an array might store a sequence of temperature readings over time. Next, we have pipe and filter. In this pattern, each module works independently and processes data continuously as it receives it. Think of it as a pipeline where each filter transforms the data before passing it to the next stage. For example, imagine a video streaming service that applies filters in real time. One module decodes the video stream. Another adjusts the brightness. And a third module compresses the stream before delivering it to the user. The modules are arranged like a pipeline, but unlike batch processing, the data is processed in real time, as soon as it's available. Lastly, there's the closed-loop process control pattern. Here, the program's execution sequence is driven by data itself. A feedback loop exists where output data is continuously used to influence the next steps in the system. A great example is a thermostat. It monitors the current temperature, compares it to the desired setting, and adjusts the heating or cooling system accordingly. This loop continues until the system stabilizes the temperature. In procedure-oriented design, the focus is on functions or procedures. The system is designed around actions that transform data, and the flow is determined by these steps or procedures. For instance, in a C program, you typically have a main procedure that calls other functions in sequence, passing data through them. On the other hand, in object-oriented design, the focus shifts from functions to objects. These objects represent real-world entities with both state data and behavior methods that operate on the data. For example, in a payroll system, you might have an employee object that contains data like name, hours worked, and pay rate. And it also contains methods like calculate pay that operate on this data. So, to summarize, depending on how you want data to flow in your system, you can choose different execution sequences, such as batch sequential for systems that handle data in chunks, pipe and filter for continuous real-time processing, closed-loop process control for systems that rely on feedback from data. And when it comes to design, you'll choose between procedure-oriented design, where the system is built around functions, object-oriented design, where the system is built around objects that combine data and behavior. Next, we'll dive into some real-world case studies where you can see these patterns in action. Now that we've covered the different types of data flow patterns and execution sequences, let's talk about where these patterns are particularly useful. There are certain applications that involve independent data transformations and have well-defined inputs and outputs. These are typically scenarios where data flows smoothly through the system without much user interaction. Let's go over a few common examples to better understand this. One of the most common examples of a system with independent data transformations is a compiler. Think about what happens when you write code in a programming language like C or Java and then compile it into machine code. The process is made up of several independent stages. Lexical analysis, the compiler reads the source code and converts it into tokens. Syntax analysis, it checks whether these tokens follow the correct syntax rules. Semantic analysis, the system checks if the code makes logical sense, like type checking. Code generation, the final machine code or bytecode is generated. In each stage, the input is transformed independently before being passed to the next stage. The compiler doesn't require any real-time interaction from the user once the process starts. And the output, machine code, is entirely determined by the input, the source code. Another common use of this pattern is business batch data processing. Let's take a payroll system as an example. Input, a company collects timesheets for all employees over a month. Step 1, the system calculates the total hours worked for each employee. Step 2, it applies salary rules and tax deductions to calculate each employee's pay. Step 3, it generates payroll reports and updates the company's financial records. This entire process happens in large batches, and there's no real-time interaction required. The inputs are clearly defined employee work hours, and the outputs are also predetermined paychecks reports. The system processes all the data sequentially or in parallel, depending on the architecture, but each stage works independently. Key point, in batch processing, data moves through several stages, but no user input is needed once the process is set in motion. It's often used in scenarios like payroll, financial reporting, and order processing. Now, why are these applications suited for this kind of architecture? Well, both examples, compilers and business batch data processing, share certain characteristics. One, no real-time interaction required. Once the process starts, it doesn't need to stop for user input. It can continue processing until completion. 2, well-defined input, output. The inputs and outputs are clearly defined before the process begins. For example, the compiler knows that the input is the source code and the output is machine code. 3, independent data transformations. The transformations or steps happen independently, one after the other, ensuring that changes or outputs from one stage don't affect how the previous stages were processed. This type of design is highly efficient for systems where you have large sets of data and want to automate the transformation process without needing users to intervene. Let's travel back in time to the era between 1950 and 1970, where one of the earliest models of data processing was widely used. This was the traditional data processing model, and it was the foundation of many early business and administrative systems. You'll often hear this model associated with programming languages like RPG, Report Program Generator, and COBOL, Common Business-Oriented Language. These languages were designed to handle the needs of business applications, like payroll, inventory management, and financial accounting. In the traditional data processing model, each subsystem or program in the system waits for the previous one to complete its task before starting its own work. Let's break this down with some key points. 1, batch processing. Instructor, data is processed in batches, which means a large group of records is collected and processed at once rather than in real time. For example, a company might collect all employee time cards for a week, process them in one batch, and then move on to the next set of records. Key point, the system handles data in chunks, and this batch of data flows from one subsystem to the next. 2, sequential subsystem execution. Instructor, in this model, each subsystem waits for the previous one to finish processing before it can begin its own task. So subsystem 1 would process the data, and once it's done, subsystem 2 begins, and so on. Think of it like an assembly line. Each task is done in strict order, one at a time, with no overlap between the subsystems. Each one has to finish before the next one can start. 3, common in early business systems. This model was common in early business and administrative systems. In those days, computers weren't fast enough for real-time processing, so it made sense to collect data in batches and process it all at once. While this model worked well for its time, it had some limitations. 1. No real-time processing. The system was designed to process data in large batches, so it wasn't suitable for applications that required immediate or real-time processing, like modern online banking or e-commerce. 2. Dependency between subsystems. Each subsystem was dependent on the completion of the previous one, so if one subsystem failed or took too long, the entire process would be delayed. 3. Rigid structure. The system was relatively inflexible. Once the batch process started, there was no way to interact with or change the data mid-process. This contrasts with today's more flexible real-time systems. Let's take a look at Figure 5.2, which shows the batch sequential architecture. This is a classic example of the traditional data processing model we talked about earlier, where data flows in batches from one subsystem to the next in a linear sequence. Here's how each subsystem works. The first subsystem validates transaction requests, such as insertions, deletions, and updates. This ensures that the data coming in is correct and ready for the next step. Next, the sort subsystem organizes these transaction records by their primary key. Sorting makes it faster to update the master file in the next stage. The update subsystem takes the sorted transactions and applies them to the master file, keeping the system's records up to date. Finally, the report subsystem generates reports with the newly updated data. This could be a payroll summary, financial report, or any output based on the batch. In a batch sequential architecture, subsystems communicate using transient intermediate files. Each subsystem processes its part, writes the result to a temporary file, and the next subsystem reads from that file. Once the next subsystem completes its task, the file is removed. This approach is commonly used in banking and utility billing systems, where large batches of transactions are processed, validated, sorted, and reported, all without real-time user interaction. The sequence of tasks is often managed by a script, which controls the order in which subsystems execute, ensuring the data flows smoothly from one stage to the next. Let's quickly go over some key domains in batch sequential architecture. Data is collected and processed in batches rather than in real time. This is ideal for systems handling large amounts of data that don't need immediate responses. The intermediate file between subsystems is a sequential access file, meaning the data is processed in the order it was written. Each subsystem reads its input files, processes the data, and writes the results to an output file, which the next subsystem picks up. There are some clear benefits to using a batch sequential architecture. 1. Simple subsystem divisions. The system is easy to divide into clear independent subsystems. 2. Standalone programs. Each subsystem can be developed as a standalone program that processes input data and produces output, increasing modularity. But there are also limitations. 1. External control needed. You need external scripts or tools to manage the processing order of subsystems. 2. No interactivity. It doesn't support user interaction during processing. No concurrency. Concurrency is not supported, meaning subsystems can't work in parallel, so throughput remains low. 4. High latency. Processing batches can introduce high latency, as each stage waits for the previous one to finish. Let's revisit our earlier example. Name, first name, Albert, last name, Einstein.